Okay, let's let them through.
Okay.
Morning, everyone.
Morning.
Okay, let's see here. Okay, here it is. Oh. Okay, let me just arrange everyone. All right, let's take some questions. I hope everyone had a good Thanksgiving. Yeah, it doesn't really make much sense if you guys are in a completely different location, but anyway, those of you who are in Ontario, I hope you didn't eat too much. Okay, if anyone has questions, just raise your hand and Syed will get to you. Everyone is too tired because they stayed up all night doing the assignment. That's good. Oh, okay, fine. Well, you'll have questions later, so I'll use that time for something else. Okay, so what we have here is what we did last time. So we defined this idea. Okay, so let's go through the logic again. So the logic went like this, so that we have two ways essentially of building subspaces. One of them is from the bottom up and one is from the top down. So what I mean by bottom up is that you build it by giving a list of vectors that span it. And so that means that the vector subspace will consist of all linear combinations where the vectors are drawn from the list. The other option is to do it from the top down, meaning that you start with the whole space and then you impose a constraint which imposes an equation, let's say, and says that I'm only going to look at those points which satisfy this equation. And then that brings you down to a subspace, and then you can impose another constraint, and then we kind of cut ourselves down to where we want to be. Okay, and the definition of a finite dimensional vector space was that it has a finite list that spans it. So that if you have a list, you can grow until you can grow a finite number of steps, and then you are the size of the entire vector space. That's the definition of finite dimensional vector space. Okay, but then we have this additional idea. So that's the idea of span and finite dimensionality. But then we have this other idea which is linear independence. Okay, so maybe I'll just summarize here. So the idea of span led to the idea of finite dimensionality. Okay, but then we have this other idea of linear dependence. Okay, and the idea of linear dependence is what is it? Remember that it's a property of a list. It says that a list of vectors is linearly dependent when you can find a non-trivial linear combination which equals 0. So in other words, that you can find that some of the vectors are dependent upon some of the others, okay, through this equation, and that equation is a linear equation, and so that's why it's called linear dependence. Okay, and we consider that to be a redundancy. It's almost like saying that one vector is on the list, but it really needn't be on the list. We don't need it to be on the list because it is a linear combination of other vectors on the list. So why is it on the list? Well, from the point of view of span, it doesn't need to be on the list, so we can remove it. And we had this idea of linear independent list. So a linear independent list means that there is no non-trivial linear combination equaling 0. And we saw from the lemma, the linear independence lemma, then that means that we cannot remove one of the vectors. We cannot say, you're guaranteed that there does not exist a vector that is linearly dependent on the previous ones. Okay, so anyway, this gave us the idea of a basis. A basis, remember, was a spanning list, which in addition to being spanning is also linearly independent. Okay, and then we proved this important lemma. The next step of the logic was that when, and this is motivated from the fact that we create linearly independent lists by firing as many people as we can without changing the span, right? So once we fired everyone, then the size of the list gets smaller and smaller and smaller until it is as tight as it possibly could be, okay? And for that reason, we were able to prove, just basically by using that argument, that the length of a spanning list, the length of a linearly independent list is always less than or equal to the length of a spanning list. Remember, a spanning list means it spans the whole vector space. Okay. So this is an inequality which always holds. And based on this, okay, we're going to define the definition of dimension. Okay, and then we get the definition of dimension. So why is that? The reason is that we would like to define, I'm being a little bit pedantic here so that you absolutely, there's no chance that you will not get this idea. So the definition that we want for dimension is that the dimension of V is the length of a basis. Okay, but the problem is, so this makes sense. This makes sense only if all bases have the same length. Okay, so how do we know that this is, so this is a preliminary result that we would need before this definition. We would need to put a preliminary result, which is that all bases of a finite dimensional. Oh, and I should say, actually, sorry. So this makes sense only if two things. V has a basis. Okay, so we first need the thing to even have a basis in the first place, and we have a lemma to that effect. Okay, so we have a lemma that says that any finite dimensional vector space has a basis, and now what we need to check is the preliminary result that two bases. So if B and B prime are bases for V, then the length of B is equal to the length of B prime. Okay, and and why is that? Well, it follows from the lemma, from this lemma here. Okay, so the proof is very simple. So B spans B prime linearly independent from the lemma means that the length of the linear independent one, the efficient one, is less than or equal to the length of the spanning one. Okay, but B prime also spans, and B is linearly independent. So using the lemma again, we get that the length of B is less than or equal to the length of B prime. So this tells us that the length of B is equal to the length of B prime. And this is the last thing that we needed in order for this definition to make sense. So we finally have a well-defined notion of dimension. Okay, so for example, okay, let's say that we take the polynomials of degree less than or equal to k, or less than or equal to n, with coefficients in a field. Okay, so this is the set of all a0 plus a1x all the way up to an x to the n, where the ai's are in the field. Okay, so this has a basis. The basis consists of, let me call it P1, or let me call them like this, P0, P1, up to Pn. These are polynomials, i.e. vectors inside the vector space, and P0 is equal to 1, P1 is equal to x, P2 is equal to x squared, and so on, up to Pn is equal to x to the n. And the claim is that this, first of all, is this spans, okay? And to see that it spans, pretty obvious, look at it here. So every element is literally of the form A0 multiplied by P0, right? So the fact that it spans is that this element here is equal to A0 P0 plus A1 P1 plus AN PN. So every element can be expressed as a linear combination of these elements, P0 up to Pn, and the fact that it's a basis, the fact that it's linearly independent comes from the fact that this A0 plus A1x plus ANX to the n is equal to 0 if and only if A0 equals A1 equals A2 equals all the way to an is equal to 0. And so this means that the only non-trivial, the only possible linear combination of these polynomials, which is equal to the 0 polynomial, is the combination where all the coefficients are 0. And that doesn't produce any redundancy. So this is totally, linearly independent. And so that means that we get a basis. Okay, and the length of this basis is n plus 1. So we conclude that the dimension of the polynomials of degree less than or equal to n is n plus 1. Okay, so that's an example to keep in mind. Okay, any questions about this whole train of logic? It's a very important series of steps which leads us to the first most important invariant of vector spaces. It's a numerical invariant called the dimension, and it's a non-negative integer. There's got to be some questions.
I have a question.
Okay, go ahead.
So
Pranav?
if we're considering the basis of a polynomial set of all the polynomials, if P0 is equal, you said A0 is equal to 0, but then how can P0 equal 1? Because
Sorry,
isn't
what? Try to tighten up your question a bit. It's a
yeah,
little
sorry, I'm just
difficult to understand.
right, because the first term, so if you have a P0 dimension 0, then that would equal 1, right? Like that's what
I'm
you wrote
sorry.
on the left.
Oh, you mean p less than or equal to 0. So if I
Yes.
took polynomials of degree less than or equal to 0, then I would have only the constant term and it would have dimension 1. Yeah.
Right. But then wouldn't the term A also be 0 then? A0 would be 1 then, right?
Yeah, I'm not sure what you're thinking. If you just put n equals to 0 in this whole description,
Right.
right, then you would get, all of this stuff would not be there, and you would have this.
Right.
Okay, this would be valid. The basis would be P0. P0 would be 1. None of these would be there. Okay,
Right.
the whole argument doesn't depend on what the value of n is.
Oh, okay. Okay, I got it. Thank you. Yeah. So I was just a little confused by the notation, but I just reread it.
Okay,
Okay, so Long Tai has a question.
go ahead.
Yeah, so we know that like in order for the the linear independent part, like where A0 is equal to A1, like all A is equal to 0.
Yes.
Like how do we get that? Or like because I read the textbook and
So,
I think
okay, this is a good question. I
yeah.
got your question. So
Yeah.
he's asking, if I have a polynomial with coefficients a0, a1 up to an, and if it's equal to 0, how do I know that the coefficients are 0 individually? Okay. And the point is that this is the definition of polynomials. Polynomial is just a list of numbers. Okay. It's a list of numbers with x as a placeholder. So to say that a polynomial vanishes, right? What is the 0 polynomial? It is precisely the polynomial whose coefficients are 0. The point is that we have to, the reason that you're finding this confusing is because you're not focusing on the definition of polynomials. A polynomial is an expression of this form where these numbers are elements of the field. These coefficients are elements of the field, okay? And the point is that we need, in order to know what 0 is, what we need is to define the addition operation. If we don't know what the operation is, then we don't know what the additive identity is. So the question is, if you define polynomials like this, what is the operation? How do you add two polynomials together? The definition of that operation is that you add them coefficient by coefficient. Right? So if I have b0 plus b1x plus bn x to the n, and if I add it to this, I'm going to get b0 plus a0 plus x times b1 plus a1 plus, you see what I mean? That the definition of the addition operation is to add the coefficients term by term. And that means that the additive identity is the polynomial where each coefficient individually is 0. So it follows immediately from the definition of the addition of polynomials. Okay, So the reason that you're feeling weird about it is because you're still thinking about polynomials as functions. And then you have to say, oh, well, okay, if I have two functions that are equal, and then if I expand them in Taylor series, how do I know that all the Taylor coefficients are equal? Wrong. These are not functions. We went over this in class before. They're just expressions of this form where we add them by adding them term by term. So you should think about that. You know, if you're still confused, then just ignore that confusion and come back to the video and watch it again.
Yeah, I will. And I remember, like, I think it's mentioned in the textbook that it will be proved in chapter 4.
No, that
So you're
I
gonna-
mentioned in class that the definition that is used in the textbook for polynomials is a special
Oh,
case and is not correct for general fields.
Okay, but it might provide some iteration.
Yeah, if you wish.
It
Yeah,
might. Okay,
but
I will look at it.
but you
Great,
should
thank you.
listen to what I'm saying over what the textbook is saying.
Yeah, I will. Okay.
Okay. Okay. Let me. Right. So. Yeah. So everyone should spend some time thinking about what dimension really means, because that's what we've just defined. Okay. Now, I want to kind of give another example, but I'm going to use the same space. I'm going to use the same space, Pn, the polynomials of degree less than or equal to n, but I'm going to use a different basis. Same space, different basis. Okay, so okay, so this is just an example, and people will get confused by this example, but it's just an example. So let's go through it, and this is something that you will have to spend some time thinking about. So suppose okay, so we know that this space has dimension. Oh, my pencil's not working properly. Okay, suppose we know that the dimension of this space is n plus 1. Okay, and we know that that polynomials determine functions. Okay, so in other words, we know that if I give you an input value, a numerical input value, and if I plug that in as the value for x, and if I follow the polynomial and expand it out, so if I evaluate the polynomial on certain numbers, I'm going to get certain numerical outputs. So suppose that I try a bunch of input values and I get the following outputs. I get a bunch of outputs, right? So there's a problem. There's a problem. There's a question that I could ask, and that is, given some probe positions, some input numbers C0, C1 up to Cn. And output values let's say B0 up to Bn. Right, so here, this is, in my picture, this is C0, and this value here is B0. This is C1, and this is the value B1. And this is C4, and this is the value B4, okay? So what I'm giving you is quintessential data. This is data, right? It's like saying that at these various times, I measured the temperature, and the temperature was given by B0, B1, B2, B3, B4, and B5. Okay, and then the question is, can we find a polynomial which fits the data, i.e. P such that P of Ci is equal to Bi. Okay, that is the problem. Does everyone understand the problem? If you don't understand the problem, ask a question now.
So on the I guess the vertical axis, B0 is the greatest value and B1 is the least and B4 is in between. Like, does that order matter at all? Because you have it like written B0, B1, B4, then B0.
Does it matter for what?
Like, and it's asking if that's significant, like to the problem, in what order they are, like in terms of value.
Well, look at the question. I want the value of the function at C0 to be B0. I want the value at C4 to be B4.
Right, but B4 is less than B0. Right.
Using what equivalence relation? You're using less than. Less than is an equivalence relation on numbers. Fields do not have an equivalence relation.
Okay.
Anything else? I'm just asking to find a polynomial that fits data. I'm hoping that this is reasonably clear what the question is here. For some reason, I'm not getting any people's faces anymore. Let me see. Okay, there we go. Can I get a thumbs up for those people who understand the problem statement? Okay, thank you. So the problem is, you know, you could think of these things as constraints, right? I'm looking inside the space of polynomials. I'm looking at all these infinitely many polynomials, but I want certain constraints to be satisfied. I want it to be the case that when I evaluate the polynomial on C0, I don't just get anything, I get B0. That is one constraint. Okay? A priori, you know, the value of the polynomial on C0 could be anything. It could be anything in the field, but I'm requiring it to be equal to a given value, B0, which is fixed at the beginning. So that is a one constraint. And then requiring that the polynomial has value B1 at C1, that's a second constraint. Okay, and so the total number of constraints here is n plus 1 constraints. Okay, so you can see that in order to satisfy all these constraints, I'm going to need a lot of freedom for a polynomial, right? I mean, I'm not going to be able to satisfy this problem with just a quadratic polynomial, because look at the data. It's going like crazy. Okay, so, and you can even tell probably that I'm not going to be able to do it necessarily with a cubic polynomial. Okay, so the question is, what is the degree of the polynomial required in order to fit this data? Okay, so you could think of the data as being like a basketball team. You know, there's all these people who are positioned around the court. And then you need to play against them. You need to find a polynomial that will take care of this data. Okay, and you need to have enough freedom in order to place people, place your team members, right? You need to place one of your team members near this guy, one near this girl, one near this guy, and so on, right? You need a certain amount of degrees of freedom in the choice of your polynomial in order to be able to move that polynomial around to fit this data. And the question is, how many degrees of freedom do you actually need? And well, the point is that, you know, the total number of constraints is exactly n+1, right? So in order to have the right amount of freedom, because you could think the person might change b0s, the b0, b1 up to bn. These values might change, and then you're going to have to change your polynomial by using your coefficients, change the coefficients of the polynomial so that you can capture these n values. Okay, so the idea is that we should guess, the guess is that this might be possible with Pn of f, since the dimension is equal to n+1, there is enough freedom in the choice of my polynomial degree n. Okay, there's enough degrees of freedom that I might be able to hit all these marks. I might be able to hit all these different values at these points. Okay, this is the heuristic. And it is true that we will be able to find a solution to these constraints in this vector space, in this finite dimensional vector space of polynomials of degree at most n. Okay. So when you think of it, so the reason, so from one point of view, the problem, okay, so now I'm going to restate the problem now in two different ways, right? One of the ways is going to be easy and one of them is going to be hard. So I want to, okay, so the reason why the problem is hard okay, is that the basis that we're used to is 1x x squared up to x to the n, okay? And so it's unclear, you know, it's unclear what linear combination of these we're going to have to take. You know, for example, so it's unclear how the choice of coefficients a0 plus a1x plus an x to the n, these coefficients here, it's unclear how the choice of the coefficients affects the value of the polynomial at c0 up to cn, right? It affects the value in a complicated way, because you need to, you know, if I make a change to these coefficients, then you need to recompute, for example, the value at c0 by putting c0 here, c0 to the n, and then making this long computation in order to figure out the value. The value is, let's say, not obvious once I choose these coefficients, right? So if you're saying, oh, I have so much freedom here, all I need to do is to ensure that at C1, the value is B1. So, well, okay, so if I plug in C1, then I need to compute all this stuff, and then I get the value, and then I need to adjust the coefficients. So you see that there's some kind of computational step that goes from the choice of the coefficients to the computation of the values. Okay, and this computational step is the thing that makes it not obvious. Okay, so here's a way of thinking that makes it easy. So alternatively, suppose we had a different basis, which was especially adapted to the positions C0 up to Cn as follows. Okay, suppose that I had, if this is C0, C1, C2. Okay, suppose that I had a basis. Let me call the basis delta 1, delta 0 up to delta n. Okay, and suppose that, let's say I'll draw a graph of delta 1. So delta 1 is the polynomial that has value 0 here, but value 1 here, and 0 elsewhere. So delta 1, okay, is defined so that delta of C0 is equal to 0, delta of C1 is equal to 1, delta 1 of C2 is equal to 0, and all the rest are all equal to 0. So it's like a delta function. It's a spike, which is equal to 1 exactly at the point C1. I mean, I understand that this is not what polynomials look like, okay? But let me make it a little more believable. So I'll remove my picture. My picture is maybe a little bit misleading. Let me draw more points. Okay, so the values at these points, sorry, this should be value 1, 0, 0, 0. So the polynomial could look, I don't know what it looks like. Could look like this. Okay. But the important thing is that its values at the special points, the points of interest, are either 0 or 1. Okay. So this is a kind of a complicated polynomial, but its values on the CI is not complicated. Okay, so we have what's called an indicator basis adapted to the points C0 up to Cn, where delta I of Cj is 0, well, I'll put it like this, is equal to 1 if I is equal to j, and 0 else. Okay. I haven't told you how to build such an indicator basis, but let's pretend that it exists. Okay, so this basis, so can we solve using this basis? Okay, we need a polynomial such that P of Ci is equal to Bi. Now, okay, so if I have to solve this problem now, you know, I'm looking at this problem, but I have a polynomial whose value at Ci is equal to 1. So I might as well use that one, right? So, so let's say if I use delta I, okay, delta I, that one is going to be very helpful because the value of delta I at Ci is equal to 1. So if I multiply delta I by the scalar Bi, then this thing will have values that I want. So this has values 0 at C0, 0 at C1, but then at Ci, it has value Bi. Okay, so you see that the indicator basis is giving me a polynomial which I can use to capture the value Bi at the point Ci. Okay, and then, so then we can conclude that if I take b0 delta 0 plus bn delta n, this is exactly the polynomial that I want. Okay, if you evaluate this thing at C0, then only this term will contribute at the point C0 because all of these others vanish at the point C0. So this one will contribute at the point C0 and it will give me value B0. This one will contribute at the point Cn and it will give value Bn. So it satisfies all the constraints. Okay, now, okay, I understand that I haven't told you how to find this indicator basis, but does everyone understand that if I had this different basis, it would make the problem extremely easy? Any questions about this? Okay, so this is a basis which is specially adapted to those points, the probe points, C0 up to Cn. Okay, so the last step is how do we build? How do we find such a basis? And this was first done by Lagrange. It's called Lagrange interpolation. And Lagrange interpolation is like the most basic method of data fitting. Okay, and the idea is very simple. So we're looking for delta I. This delta I should have value 1 at Ci and 0 at Cj. J is not equal to I. So how do we produce? Okay, so we're just going to build it by hand. We're just going to create it by hand, this basis. So how do we ensure that a polynomial has 0 value at a bunch of points? How do we ensure that a polynomial has a 0 at the point 3 and a 0 at the point 5? Anyone?
Just make them roots.
Factors.
Make them roots, make them factors, right? So if I want a polynomial that has 0 value at 3 and 5, I just produce this. Okay, so what does that mean? That means that I can take x minus C0, x minus C1, x minus Ci minus 1, but then I do not put x minus Ci. I don't put that. And I want x minus Ci plus 1 all the way to x minus Cn. Okay, so I don't, I remove this here. Okay, so this thing will have at all Cj, it'll have zeros. You see that? Okay, but then what about the value at Ci? That's the problem. What value does this thing have at Ci? Well, at Ci, it has value x minus, sorry, Ci minus C0, Ci minus C1, all the way. You know, you just plug in Ci, and you'll see what value it has. So it'll have that value, but I don't want it to have that value. I want it to have value 1. So I just divide by that value. So I divide this polynomial by a number, Ci minus C0, Ci minus C1, Ci minus Ci minus 1, Ci minus Ci plus 1, Ci minus Cn. And that guarantees that delta I has the property we want. Okay, it has zeros at all of the Ci's except all of the Cj's except for j equals I, and the value at Ci is equal to 1. Okay, now there's a problem with this. There's a possible problem with this, which you should be worried about. I'll get to your question in a second. So the problem is that whenever you divide by something in the field, you have to worry about whether that is 0 or not. So it is very important that Ci is not equal to C0, that Ci is not equal to C1, and so on. So what does that mean? That means that I need all of these points, all the differences between the points to be non-zero. I need the points to be distinct. That's the thing that I need. So this will work if the CIs are pairwise distinct. Okay, so we need this in order for this to work. Okay, so I produced now a list of polynomials. Okay, and so just to review or summary. Okay, we fix pairwise distinct elements of F, C0 up to Cn. And then we create basis be adapted to C. With the property that delta I of Cj is equal to 1 if I is equal to j and 0 else. Okay, and so that's what we did. We gave a formula. Delta I is the product of j not equal to I of x minus Cj divided by Ci minus Cj. You could put it, to be more precise, j goes from 0 to n, and j is not equal to I. So this is the basis that we need. And then the solution. So the fit to data is just the sum of bi delta I. P of Ci is equal to bi. And this is in Pn of F. Okay, so this is the summary of Lagrange interpolation. Okay, now just a remark. How do we know this is a basis? Okay, so in order to know that this is a basis, okay, I'm going to show that it's linearly independent. Okay, why is it linearly independent? Well, it's this basis is an indicator basis, right? So if I take, suppose that I take, so if we have if we have a bunch of coefficients, a0 up to an, are such that we have a linear combination of the basis elements of the, of the list of vectors. If we have a linear combination which equals 0, okay, so if we have a linear combination equals 0, I want to prove that the coefficients must all be 0. In other words, that there are no redundancies. In other words, that it is a linearly independent list. Okay, so we want to show that all the AIs must be 0. Okay, and this would imply that the list BC is linearly independent. Okay, but how do I prove this? Well, it's easy because this is an indicator basis, right? So if I evaluate this polynomial at the point C0, then what am I going to get, right? So if, let me just call this polynomial something, let's call it F. But F of Ci, or let's say F of Ci is equal to, so if I evaluate it at one of my special points that my basis is adapted to, then you see that delta 0 at Ci is going to be 0. And all of these will be 0 except for the ith term. And the ith term will give us exactly AI. So this will be AI. So this equation implies that the value of this polynomial at the point Ci give you the coefficients. But if the polynomial is 0, then when we evaluate the 0 polynomial, we should get 0. Okay, so this proves that this is linearly independent. Okay.
Should that be for all I or for all 0? Right before the end.
This
So
is true for all I.
Yeah, and you have like the for all bit at the end.
Oh, sorry. Yeah, for all I, we get this.
Okay. Yeah.
So this proves that it's linearly independent. And its length is n plus 1. So that means that it must be a basis. Why? The reason is because we already showed before that the length of the standard basis, the length of the standard basis, the length of the standard basis is n plus 1. N plus 1 is the dimension of this space. So if we can find a linearly independent list which has the same length, it must be a basis. Okay, so anyway, this is the full argument. So we have now changed. You should think that if you wanted to think geometrically, you should think that the space of polynomials is some kind of space, and we have the standard basis 1 x squared for this space. But now we have this alternative basis. So you could imagine that the alternative basis is like this, delta 0, delta 1, and delta 2. We now have two bases. Well, we have two different bases for the same vector space of dimension n plus 1. And this is the vector space. This is basically the simplest vector space that you would use in order to model data when you have, a certain number of data points. Then that will determine the dimension of your space of polynomials, the degree of the polynomials, and then you could find a polynomial that fits your data. And that might be useful because then you can evaluate the polynomial at other points and make predictions about what the data might be at the other points. I'm not saying this is a particularly efficient or good way to do it, but it's not bad. Okay, any questions about this, this whole method? So this is just illustrating the power of choosing different bases, making a problem easy by changing the bases. Any questions?
Shuji, you have a question?
Yeah, I have a question for.
Yeah, go ahead.
So we write delta I equals the product of something, but what if like Ci is equal to Cj at some situation? How could we deal with this situation?
So I said that this will work if the CIs are pairwise distinct. So I'm explaining the procedure for a situation where you are giving data at different times or different values of the parameter.
Oh, I see. So like
that's the setting of this problem. I'm not explaining. Well, I'm not sure what kind of data you are thinking of, but the CIs must be distinct in order for this to work.
okay, so this is the setting like when this method will work.
Yeah, correct.
Oh, okay.
If you have two data points taken at the same time, but with different values, yeah, then you might want to do some statistics on those data because you're not going to fit that data with a single function.
Okay, thank you.
You're welcome.
Okay, Juan, you have a question?
Yeah, I'm still not quite sure how you arrived at the denominator and the. Sorry, can you scroll up? Sorry. Yeah, how did you
But
get
okay,
the
but
C?
sorry. So do you see how I got the numerator?
Yeah, I see that.
Why? How did I get the numerator?
I think. Yeah, I got quite lost in that part.
But what about the numerator? Do you see that? Do you understand why? Okay. I need to find a polynomial that vanishes at C0, C1, C2. It vanishes at almost all the points, but it's equal to 1 at a single one of them. Does that make sense?
Yes.
So in other words, I'm looking for a polynomial here, which has a 0 here, 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 and here, but not here.
Yeah.
Okay. So what do I do? I just enforce that there's a 0 at C0, right? So that's why the numerator has a 0 at C0, a 0 at C1, a 0 at Ci minus 1, and I skip over Ci because I don't want a 0 at Ci. So I'm gonna multiply this out, and you can see that this is how we build a polynomial that has zeros at the prescribed points, C0, C1, and so on. Explaining how the numerator is arrived at.
Okay. Yeah.
Okay, but then the problem is that I ensured that I have zeros in the right place. But now I need something else. I need a normalization. I need to figure out what is the value of this thing at Ci, and is the value equal to 1, or is it equal to some random number? Well, okay, so in order to figure that out, all you need to do, right, is plug in the value Ci. If you look at the value of the numerator at Ci, what you get is Ci minus C0, Ci minus C1, Ci minus Ci minus 1, etc. You're going to get the product of all these things. It's going to be some complicated expression. Okay, and whatever that complicated expression is, I don't know if it's equal to 1 or not. So if it's not equal to 1, just divide by that number, whatever that number is.
Oh, okay. Okay.
So that way it's equal to 1.
I see now. Okay. Thanks.
Okay, we're going to take a break, but I'm going to give you a quiz. So let me it's just a true or false thing. And I will give it to you as soon as I can find, this thing doesn't want to give me, oh, there it is, okay. Okay, here we go. The poll is in progress. Give me a thumbs up if you see the poll. Okay, go ahead. You have 5 minutes. At 5 minutes, and then I'll close the poll. I'll mute myself for now.
So there are a few questions in the chat about how much longer they have.
There's 1 minute remaining. Okay, I'm going to close the poll. You should submit your answers now. 10, 9, 8, 7, 6. Next time I'll put a timer. 5, 4, 3, 2, 1. Okay, so we see the poll results here. Okay, let's take a look. We're going to have a break, by the way. So you'll come back at 12:20. We're going to start the lecture again at 12:20. But let's just look at this. Suppose that we have a linearly independent list of vectors. If we add another vector to the list, the new list will be linearly dependent. Okay, so this is false because, for example, you could have a non-zero vector, and then you could add another vector to it in 2 dimensions to make a basis, right? So if I'm in 3 dimensions and if I have one vector, which is non-zero, that's already linearly independent. Then if I add another vector, which is not in the span, that will be a linearly independent list of 2 vectors. And then I could even add a third one and it still would be linearly independent. But once I get to a basis, then it's true that if I add another vector, then it would be linearly dependent. So that's why it's false. Okay, and let's look at the next one. So I have a list of 3 vectors which are linear. So it says the list is linearly independent. That's definitely true. You can kind of see that the first one, I mean, this one is in 3 dimensions, so it's easy to even visualize that the first vector is non-zero, the second one is not in the span of the first, and the third is not in the span of the first 2, right? So by the linearly independence lemma, or just by your visual sense, right? These are 3 vectors which are not in the same subspace. Okay, and then okay, and then the next one, oops, sorry. The next one says the subset of vectors of the form xxx, where x is in R, is a linear subspace of R3. That is true, and 96% of you got it, so I'm not even going to bother saying why. Okay, number 4, the intersection of 2 linear subspaces is always non-empty. That is true because, even if I was considering 2 one-dimensional subspaces which were distinct, they still intersect in 0. 0 is always present in any subspace, and it is the intersection of 2 linear subspaces is always a linear subspace, so 0 is always there. So it could be more than 0, the intersection, but it has to be at least 0. This is extremely important, this fact. The span of the empty list is the 0 subspace, yeah, but that's not really, that's not really on the list. I could have put that, but that's a more tricky type question. Okay, number 5, the intersection of 2 affine linear subspaces is always non-empty, and this one is false, as 81% of you saw. And the point is that, if I take the whole point of an affine linear subspace is that you start with a linear subspace and then you move it off of itself. You translate it. Okay, so if the original was a line going through the origin, then I could take that line and move it off of the origin and get another parallel line. So, and that's not a linear subspace, but it is an affine linear subspace. So of course you could have 2 parallel lines which don't intersect. Or even in 1 dimension, you could have different points. The different points are linear, affine linear subspaces. every single point in a vector space is a zero-dimensional affine linear subspace. And if you could, of course, you could have 2 points which are not intersecting. So okay. Well, take a screen cap of the questions or something, because I'm going to take them off in a second. Okay. Okay, so I'm sorry if that was stressful. You have 2 minutes to lie down on the ground. Just lie down on the ground, take a deep breath, and we'll start again in 2 minutes. Okay, see you later. Okay, hi everyone. Okay, so for the rest of today, I want to explain. I'm going to put these notes up as well. So this is, it's basically a skill or an algorithm that you need to learn. It's called the Gaussian elimination algorithm. It's the most important process that you should learn in linear algebra. And it's probably the most often used computation in all of algorithms. So, okay, so what is this thing doing? So, so the purpose of the algorithm, I'm going to go through this step by step, but the purpose of this algorithm is that it takes a list of vectors that you provide, and it rearranges it. It produces a new list from it, which is easier to understand. So it somehow puts your data into a more digestible form. So let me make a more formal statement. So the input of the Gaussian elimination algorithm is a list of vectors, but it's not just a list of vectors. It's a list of vectors together with a preferred basis. So for example, you could give me a bunch of polynomials, and then I'm going to use a particular basis. So that could be the standard basis 1x, x squared, and so on, or it could be one of my preferred bases. Whatever it is, I'm going to analyze the list using the basis. That's what I'm going to do with this algorithm. And the output, okay, is a different list of vectors, but it's a list that has the same length and it has the same span, but the vectors are different. Okay, but the claim is that the new list, the output list, is better in some way than the input list. So why? Why is it better? Well, the point is that it looks better in the basis that you are using. So let me explain what that means. So suppose you give me a list of k vectors. Then I can take each vector and I can write it as a linear combination of the basis. So that means that the data of this vector v1 is really captured by these coefficients a1, 1, a1, 2, 1, 3, 1 up to 1n. So this is the coefficient, the nth coefficient of the first vector on the list. So in other words, if we all agree on the basis, then giving the data of this vector is the same as giving these numbers, a11 up to a1n. And then I do this, I expand in this way for every vector on the list. So I have k vectors. That means that I will have k collections of n numbers. So I'm going to have a k by n matrix of numbers, a11 all the way up to akn. Okay, now the convention for labeling the entries of a matrix is exactly the one that I'm drawing here. The first number, okay, it labels which vector it is that I'm expanding. Since this is the first vector, every number here has a 1 in front. 1, 1, 1. That's the first row. So the number 1 indicates the first row. The number 2 here indicates the second row, and so on. So it's always of the form a row column. Which row am I in? Which column am I in? Okay, to remember this, you could sometimes use like remote control as a mnemonic, or Roman Catholic, like a certain very famous person in the news these days. So however you want to remember it is fine with me. The point is that, yeah, we do it like this. So there's k rows and n columns in this matrix. The point here is that the data of this matrix of numbers, k by n grid of numbers, is that it is the same data as simply giving this list of vectors. But in order to write it in this very explicit way, I need a basis. Okay, so I have a k by n matrix of numbers. Again, the number of rows and the number of columns. Always the first is the number of rows and then the number of columns. And so I have these numbers which are indexed by two numbers I and j. I ranges from 1 to k, j from 1 to n. Okay. Any question about the input? What the input is? If there's any confusion about what you need to give me in order to begin the algorithm, let me know now. You need a matrix like this. Or if you want to be a little more fancy, it's a list of vectors and a preferred basis. It's up to you which way you want to think about it.
I don't understand why we need the basis to make the matrix.
Well, if I give you a bunch of vectors, right, then the vectors are vectors. They could be vectors in the space of polynomials, for example, right? And how am I going to get these numbers out of a polynomial? I mean, these numbers, you have to take the polynomial and write it as a sum of components, right? Like, let's say you write it as a0 times 1 plus a1 times x.
Yes, I understand.
Okay, if you don't have a basis to expand this thing out with, you will not get numbers here.
Thank you, I got it.
Long tie, you have a question?
Yeah, so Aij, like, so if we have like a matrix with like 4 rows and 6 columns, then we write A46.
So you're saying if this matrix has 4 rows and 6 columns, right,
Yeah.
then I will range from however many rows you have. So it will range from 1 to 4, and j will range from 1 to 6. And you can have any combination, any number from 1 to 4, and any number from 1 to 6 can occur here. And you'll be zeroing in on one of the entries of the matrix.
Oh, but isn't it kind of confusing? Like when you have like with 2-digit, like for example, like with 11 rows and 12 columns. So it will be like I don't know, A11.
Yeah.
And 12, like A.
So you're confused because it could look like 1,200,
Yeah.
1,221, right?
Yeah.
Okay. Well, if you're in a situation like this, then put a comma and
Okay.
put.
That's better.
Okay.
Okay, thank you.
But you know, don't provoke me to give you problems which have more than 10 entries in the rows. If you insist, I will do it, but I never got that question before. It's a good one.
Yeah.
In a computer, you would have to indicate that it's an ordered pair. So you would have to put some kind of separator for the. Okay. Now the output. The output is another list of vectors. Okay. So the output will be another matrix. The input and the output have the same format. Okay. But the output is highly constrained. It has to look like this. It has to be that it's it has to be so that it has the same span. Okay, so it will define the same subspace, but the rows of the matrix will look a lot simpler. It will be in either what's called row echelon form or reduced row echelon form. Okay, echelon is the French word for what? Does anyone know?
Stair.
Yeah, stair. It's like a staircase. Okay. So the way it looks is that if you look at the first row, okay, there may be some zeros, but at some point the zeros will stop and I'm going to get a 1. And then after that could be anything at all. And then the second row, 0, 0, 0, 0, 0, and then a 1. And then whatever, something. It could be any numbers after the 1. So the notation here is that I have a big 0 here, which is all zeros, all underneath the staircase. And then I have a staircase where at every stair, I have a 1 in the corner. 1, 1, 1. But above this, it could be anything. Anything here, anything here, anything, anything, anything. Okay? This is called row echelon form. The first non-zero number in the row is 1. Okay? And in position ti, and ti plus 1 is greater than ti. So that means that the next row has to be that the 1 is more to the right of the previous row. So it really has to be a stair going down, at each row, it will go, there will be a stair at each row. Okay, so, and then reduced row echelon form is a little more constrained, where it's the same as before, except above each echelon, so above each number 1, you have zeros. But then everything else can be as before. Okay, so this is the point, is that we are going to take a random, we're going to take a random k by n matrix. In other words, you're going to give me any list of vectors, list of k vectors, and I'm going to do operations on it in the algorithm, which is I'm going to massage it without changing the span, meaning without changing the subspace that is determined by this, but in such a way that it's going to be in this form. Okay, and it'll be very useful to have a new spanning set like this in this form. Okay, and we'll see why in a moment. Okay, so this is the input and the output. I'm going to explain the reasoning behind this and the purpose of it in a moment, but I just want, you should be able to understand the input and the output completely clearly. Any questions about this?
So Dixchant has a question, or maybe not anymore.
Oh yeah, I just wanted to ask, so you have defined an input and an output, but like, how are we getting the output in the first place?
Yeah, I haven't told you.
Oh, okay, so it's arbitrary for now. Okay.
Well, I haven't told you yet. You have to wait.
Right. So
I'm concerned about whether you know the input and the output.
Okay.
Okay, so this is like a problem statement. Given a list of vectors and a basis, okay, can you produce me another list of vectors, same length, with the same span, okay, such that if I expand it out in terms of the same basis, I'm going to get something in reduced echelon form. Okay, so it's a problem. Okay, so what's the purpose of this? So the purpose of the Gaussian elimination is to make it easier to understand the span of the original list. Okay, for example, is it true that the list is linearly independent? Okay, it may not be obvious from the given data that it is linearly independent or not. Can you tell that V1 up to Vk are linearly independent? Okay, but after you do the Gaussian elimination and you look at the output, then it will become completely obvious whether they were linearly independent. Okay, if I want to know the dimension of the span, it will become very obvious what the dimension of the span is, right? Because, for example, if I give you a matrix like this, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? It may not be obvious what the dimension of the span is. But if I give you a matrix that looks like this, okay, then look at the rows. I have 0, 1, 0, 0, I have 0, 0, 1, 0, and I have 0, 0, 0, 0. Okay, so if I look at the span, then I can tell this is the 0 vector. So this will not contribute to the span. This and this are linearly independent. So I can tell right away that these 3 vectors, right, because of the way the matrix looks, it's obvious that the span of these 3 vectors has dimension 2. Whereas this one, it's not clear whether the span has dimension 1, 2, or 3 because of the complexity of the way it looks. Okay. The other thing that it makes it easier to do is to find a basis for the span. It makes it completely easy to find a basis for the span because the original list of vectors might be overkill. There might be a lot of redundancies and you might want to reduce it, right? And maybe the linear independence lemma is not an algorithm, right? It doesn't say exactly how do we determine whether a vector is in the span of the previous. The linear independence lemma, it's a useful lemma, but it's not an algorithm. Whereas this one will make it completely easy to find a basis for the span of these vectors. And then the other thing is that if I give you two lists, how do I know whether the span of one list and the span of the other list are the same? All of these questions can be easily solved with Gaussian elimination. And the other thing that it does is solving equations, systems of equations of homogeneous linear equations or inhomogeneous linear equations can be completely solved in a completely easy way using Gaussian elimination. So solving linear systems of linear equations and all of these other problems, they're all equivalent to Gaussian elimination, or at least they're made simple when you know how to do Gaussian elimination. Okay, so that's the purpose. It's the most important algorithm in linear algebra. Okay, and what is the algorithm? Well, the algorithm is that you take these vectors, okay, these vectors which are represented by rows in this matrix, and you need to do certain operations on them. I'm going to apply certain elementary operations. It's like, you know, there's basically like certain allowed moves, like with a Rubik's Cube, right? You have an initial state of the Rubik's Cube, which is complicated, and you know what the final state is. It has to be an echelon form. And then there are certain very simple moves that you're allowed to do. You're allowed to turn certain faces, and you can just choose which face to turn. And that's all you're allowed to do. You're allowed only these elementary moves. And then you need to figure out what order to apply these operations in order to arrive at your endpoint, you know, your desired endpoint. So that's what it is. It's a very simple Rubik's Cube solver. That's what this thing is. So what are the basic moves? The basic moves have a name. They're called elementary row operations. Okay. Okay, now, before I tell you what the operations are, think about what we need out of these operations. Let's look at the output. We need the output to be a list that has the same span. Okay, so that means that if the algorithm consists of just applying certain basic moves, we need to make sure that these moves do not change the span. As long as the elementary moves don't change the span, then when I apply many of these elementary moves, the span won't change, right? So in order to ensure that at the end I will have the same span, I'm not going to bother figuring out what the span is at the end. I'm just going to make sure that all of my operations do not ruin the span. That's the technique. Okay. Okay, and then I want to make sure that my operations simplify and put it into row echelon form. So that's the task. Okay, so there are three basic operations. Okay, the first one is called switching. Okay, and this is, again, it's really important that we are dealing with lists, not sets of vectors, but lists. Okay, because I have this list, okay, there's going to be an ith and a jth entry, and I could just switch these two. So you see, I said that I just wrote it informally as the switching of row I and row j. Okay, so this elementary row operation replaces Ri with what used to be Rj and replaces Rj with what used to be Ri. The next operation, and of course you can see that doesn't change the span because basically I still have the same vectors. Okay, then the next one is that you could take a non-zero scalar and you could multiply one of the vectors in the list by lambda. So this is the row operation that takes the ith row. Don't be confused by the fact that I'm calling this the ith row. Remember that this is a list of vectors, and the vectors are represented by rows, right? So Vi is the ith row of this matrix. And what I'm doing is I'm multiplying it by a number, and that number has to be non-zero. Okay, so then the next, so these two are pretty easy. The third one is less obvious. It's called the shear transformation, and what it does is it takes a vector Vj, and it adds it to another vector. So I'm going to keep all the vectors the same except for Vi. Vi will be modified by adding a multiple of Vj. Any multiple at all will do, including 0. Okay, and the idea is that I've added Vj to Vi, but of course, if you take linear combinations of these things, if I had originally a linear combination which involved Vi, now I can still get it using Vi plus lambda Vj because I have Vj available. So if I take, what I'm trying to say is that it should be obvious that the span of this list is the same as the span of this list, because since Vi plus lambda Vj is in this list, and since Vj is in this list, then I can take a linear combination of this and this, which produces Vi. I can take this vector minus lambda times this vector, and I will get Vi. So Vi is in the span of this list. Vj is in the span of this list, and all the other vectors are in the span of this list. So it's clear that the span of this list is the same as the span of this list. And I've denoted this by saying that rho I goes to rho I plus lambda times rho j. So I'm multiplying rho j by a number, and I'm adding it to the row I. And I'm getting a new rho I, and I'm doing nothing to rho j. Rho j stays by itself. So, okay, so each of these operations, okay, so each operation is reversible, first of all. Okay, so if I switch Vi and Vj, I can obviously switch them back. If I multiply by lambda, I can multiply by lambda inverse because I'm in a field and there are multiplicative inverses. And if I shear, then I can shear back because I can always replace this vector by itself plus minus lambda times Vj. So I can always undo the shear. So these are reversible operations which do not change the span. Okay, but we are changing the list of vectors. So that means that the matrix will change by switching, scaling, and shearing the rows. That's it. Those are the operations. And it's obvious, or at least you can check, that they are all reversible and they don't change the span. Any question about the basic operations of this procedure?
Okay, so G Cow has a question.
Yeah, go ahead.
My question was about you mentioned we can use this to check if the span of two lists of vectors are the same.
Yes.
So are you saying the RRE form of a span of list of vectors is unique?
Well, what do you mean? What do you mean by unique?
Meaning that if the two lists of vectors, they share the same span, when you do all of these operations, you will always end up with the same matrix.
No, I mean, I think you're trying to jump to some conclusions. I'm telling you here what the purpose is, but this requires some thought about how you're going to use this algorithm to solve all these problems. Okay, so I'm going to describe you an algorithm that takes this input to this output. Okay, I'm not going to show you the applications yet. Okay, but the important thing here is that every time I apply these operations, the span remains the same, but the vectors that do the span change. Okay,
Okay, thank you.
And
Okay, Harsh,
Harsh,
you have a question?
Hi, I didn't really follow why the fact that it's a list, not a set, is significant for the switching operation.
Okay, so let me ask you, if you have your vectors and I tell you take the third vector and the fifth vector and switch them.
Yes.
Okay, so you need them to be a list in order for you to follow my instruction. Otherwise, you wouldn't know which is the third vector and which is the fifth vector.
Okay, yeah, thank you.
Right? They need to be ordered.
Okay, yeah, thank you.
If you switch two elements of a set, you're not doing anything to the set because the set does not have an ordering in it.
Yes, I understand.
Okay, so the point is that when we write these vectors as a matrix, we are ordering them, right? That's the purpose of drawing them in a square picture like that, a rectangular picture, that there's one on the top and there's one underneath and so on. Okay, Kanav?
Okay, so just about the three different basic transformations.
Yes.
So
yes.
So when you say it's successively applied, does that mean one step is applied to each element in the list?
You see here, this is the list of vectors.
Right.
Okay. And here is this is my input list.
Mhm.
This is the output list.
Right.
So you give me a list. This operation will switch the I and the jth elements of the list and output this new list.
Okay.
Okay.
And do they have to be
Now
consecutive?
you could there are many operations depending on which I and which j you choose. So if you wanted to switch the first two rows, then you would do the switching of R1 and R2. You could switch R1 and R3, R1 and R5, R3 and R6.
Okay.
Right? Those are all the possible switching operations that I'm permitting you to use on
Okay.
your list.
So
Okay?
when you
have
say
the scaling and the shearing.
so when you say successively, like what are you implying by does that mean like you have to do all three each time, or like what?
Did you ever solve a Rubik's Cube?
I have
Or
one.
try?
I've tried, yeah.
Okay, so when you try to solve a Rubik's Cube, you turn this face, you turn that face. Every face can be turned. Do you agree?
Okay.
So those are the fundamental operations. Now,
Okay.
if you have to solve it, you have to turn the ones in the right order at the right time, right? So I haven't told you that yet, how to solve, but I've told you which moves you're allowed to make. I've told you the rules of the game.
Okay.
I've given you the rules of the game, and now you can go away and try to figure out how am I supposed to use these rules in order to get the input into the output that he's asking me for.
Okay. Thank you, sir.
Okay. So now I'm going to tell you, okay, so I'll tell you how you're supposed to do it. Okay. So the first step. So now I'm going to tell you which sequence of operations you're supposed to do when you're faced with a matrix. Okay, so first you look at the rows and you find a row, you find a vector that has the earliest non-zero coefficient. Okay, so in other words, if I have something like this, okay, then you see that this row has zeros up to entry number 2. This one has zeros up to entry number 3, and this one has an entry which is non-zero at a very early stage, stage 1, right? So I'm finding a vector that has the earliest non-zero coefficient, okay? And this one is the one, it's V2. Doesn't matter that it's 1, it could be a 5. Okay, so I have a non-zero coefficient in the first position. That's earliest for this list of vectors. So now I want this one to be first. I want that early coefficient to be up higher. So you switch it with V1. Now, there might be many vectors that have an early coefficient. So what you just have to do is pick the first one you find and just put it on top. Okay. Now, when I do that, when I put V2 into the first position, if I switch these, so let me take this and put it up here. Okay. Now that's my new V1. Okay, now I see that the row that has the earliest non-zero coefficient is on top. Okay, so that's good because now it looks a little more like my staircase, right? I want the earliest non-zero coefficient to be here on the top. Okay, but I don't want the leading coefficient to be 5. I want it to be 1. So I need to scale that row. Oops. So what I'm going to do now is I'm going to scale this by 1/5. Right? And I'm going to get 1 2/5, 0 1 7/5. Okay, so now I modified my original list so that the earliest non-zero coefficient occurs in the first row and with leading coefficient 1. Okay, that's part of step 1. Okay, and now the problem is, okay, there might be some other vectors here which I didn't tell you about. Let's say this one, 7 6 5 3 1. Okay, so I found a vector that was originally the second vector that had a very early non-zero coefficient, and now I put it first. Okay, but further down the list, there's another vector that also has a non-zero coefficient in the same early position. Okay, so I could have chosen this guy to put at the front, but I didn't. I chose this one. Okay, and so that means that this echelon, okay, is staring down, and it sees this as its enemy, because if you look at the echelon form, each one of these echelons looks down and sees only zeros, zeros, zeros. Okay, so this echelon does not like to see anything non-zero beneath it. And so what we're going to do is we're going to replace this row by this row minus 7 times this row. I'm going to do a shear. Okay, so now V4, I mean, normally you don't bother writing tildes. I'm just going to replace V4 tilde with V4 double tilde, which is going to be taking V4 minus 7 times V1. Let me just relabel these as V1, V2, V3, V4. And my new V4 is going to be V4 minus 7 times V1. That's a shear. I'm using V1 to modify V4, but I'm leaving V1 alone. I don't do anything to V1. So what happens when I do that? I'm going to get, in the first position, I'm going to get 7 minus 7 times 1. So I'm going to get 0. And then I'm going to get 6 minus 7 times 2/5. Okay, so I'm going to get 6 minus 7 times 2 over 5. That's going to be in the next position. Then I'll get 5 minus 7 times 0. So I'll just get 5. And then 3 minus 7, I'm going to get minus 4. And then 1 minus 7 times 7/5. So I'll get 1 minus 7 squared over 5. The particular values are not that important, but I'm just saying that I've replaced the offensive 7 leading vector by this sheared version. Okay, I've chopped off the 7 part, and now this 1 looks down and sees all that it's conquered, and it's happy, and the span is unchanged. So we have successfully obtained an echelon. That's the end of step 1. Okay, so the output of step 1 is the new first vector. The new first vector is the scaling of the early bird vector that we found. And then the new elf row is going to be V1 minus this, and the same goes for all the, I'm basically just rewriting the three steps that I just did. And here you can see what the result is. I get an echelon and zeros beneath it. Okay, so after step 1, this is what it looks like. Okay, but now I can just look at V2, V3, V4, right? And now I'm back to the drawing board. I have the same situation. I've dealt with the first echelon. All I need to do is repeat the process for this new rectangle, right? So I'm going to do it again. And after step 2, what I'm going to see is an echelon in row 2 somewhere, because it could be that there's zeros here, and you have to look for the early bird in this list. I need to find which vector here has the earliest non-zero coefficient, and I need to put it in the first row. So that's what happened here. I looked through and I found this row that had an early non-zero coefficient. I put it first, and then I cleared out, using shears, I cleared out all of the rows beneath it. Okay, so step 2 is just to repeat this procedure for the rows after 1. And then step J is that you just keep doing this. So after k steps, the algorithm arrives at the row echelon form. The reduced echelon form. Okay, so if I keep doing this, I will get exactly what I want to, which is this. I get an echelon here with zeros, and then an echelon in the second row, an echelon in the third row, and everything beneath is 0. Okay, so that involves a switch, a single switch, okay, and then a single scaling, and then potentially a lot of shears to produce each echelon. Okay, so you can even count the number of operations that this will take. Okay, but then once I have it in row echelon form, I keep forgetting. Yeah, once I have it in row echelon form, I would like to reduce it to be even simpler. That's optional. Okay, you may or may not want to go to reduced row echelon form. And this is saying that this psychopath in the echelon who killed everything beneath it, now we're going to use him to kill all of the people above it. So we want to get zeros here, right? So you can see how to do it. If there's some kind of innocent person, innocent coefficient in the first vector minding its own business, okay, but then this person comes along and says, I just arbitrarily, I just want to convert you to a 0. The way that you could do it is by replacing the first row by a shear, using the second row to get rid of whatever the coefficient is here and make it into a 0. Okay, and then you'll be left with this this situation where you have the echelon and you have no other 0 coefficients above or below. Okay, that's optional for you, but it can be very useful for certain purposes, which we'll get to. So that's what I mean here by going from row echelon to reduced row echelon is called the backward pass. And the way that it works is that you look at this and then you start from the last echelon. You use the last echelon, let's say this one, to clear everything above it using shears. And then you use this echelon to clear everything above it, and you move back to the first echelon. So it's called the backward pass because you start at the bottom of the matrix and you make replacements of the vectors above it. Okay, but basically the situation is pretty simple. You use you use VK to shear all of the vectors before it so that their coefficient in the position where the echelon is non-zero or equals to 1 gives 0. So you see here that the first row is replaced by it remove a multiple of VK. All of these rows before VK are changed by shear, but the kth row is not changed. And that's the psychopath that killed all the people behind it. So that's it. That's all it is. So I'm going to leave it there. And then on Thursday, we're going to see how useful this is. But for now, you should really like go over this carefully, do an example. I'm going to do an example on Thursday. Yeah, go through this in great detail. Okay, I'll take some questions, but that should be it for today.
Okay, so
I'll put this up later today.
Anatoly, you have a question?
Yeah. So in your third step of the forward pass, of step 1 specifically, actually.
Step 1?
Right.
Oh, sorry. Step 1. Yeah, step 1.
So you're multiplying, you're replacing VM by VM minus AMI, but why are you multiplying AMI by the multiplicative inverse of AEI if we've already
Well, I'm
dealt
just
with that
doing
earlier?
it all. I'm kind of writing the output of step 1 all at once because
Oh.
remember that we needed to take the early bird and scale
Right.
it by its leading coefficient, right?
Oh, so it's not like you're doing it one after the other. You're essentially doing it like in like one step, I guess.
Well, I'm basically explaining the input going to the output after step 1 is complete,
Okay.
and that's what it looks like.
I see. And just to confirm my intuition, the backwards pass is essentially the same thing as the forward pass, but you're just doing it from the back and from the bottom, right?
Yeah, correct.
Okay, cool. Yeah. Thank you.
You're welcome.
Okay, so Lauren, you have a question?
Yeah. So I have a question about the backward pass. So why should we start from the bottom?
Well, the reason is that let's say that we want to clear everything above here, right? Or let's say I want to clear everything above here. Suppose there's an entry here that I want to make 0. Then what I would do is I would replace the first row by the first row minus some constant times the second row, right? So for example, if this was 3, then I would replace V1 by V1 minus 3 times V2. Okay, and I would leave V2 alone. Okay, and what this would do is it would multiply this number by 3 and subtract from this row, and it would make this entry 0. Okay, but the problem is that what about this guy? What if now I have 6 and 3 or 1 here, right? In order to clear these two, I'm going to have to replace V2 by V2 minus 6 times V3, and I'm going to have to replace V1 by V1 minus V3. So because I'm now screwing around with V1, that means that if I had cleared this first, and if I had row 1 all nice the way I wanted it, but now if I'm going to clear this one, and I'm going to change V1 again, and it may create, oh, actually, sorry.
Influence.
Just remove from there, remove from there.
You'd be subtracting zeros, so
yeah, that
wouldn't be the same.
That would still work. That would still work, but I guess the problem is just
the later columns get just like messed up.
Yeah, I guess the point is this, that you could do it that way if you wished, okay, but the problem is that if you do this one first, right, if you modify this one first, then the particular entries here in the next column are going to change, and therefore the particular shears that you need to do, okay, will be modified. Which shear you have to do for the third column will be affected by what you did in the second column. if you wanted to specify a list of shears which doesn't depend on what you had to do, then you should do it in the backwards direction, because then the idea is that once you clear this out, then when you clear this one, the values are not affected, right? Because when you clear this out, you're going to be subtracting, let's say, V3 from V1. But if you look at how that affects this column, V3 has a 0 value here. So that means that this number will not change if you did this one first. So in other words, if I do it in the reverse direction, I know what the coefficient will be in my shear for this step in the reduction. So it's easier to write down the algorithm because all the coefficients are determined.
Yeah, I see.
You could, of course, figure out what the numerical values of the shears should be if you go in the forward direction, but that's going to involve more computational steps to figure out those coefficients. I think if you count the number of operations, you'll see that there's fewer when you go in the reverse.
Right. Thank you.
Okay, so Charlie, you have a question?
Yeah, I'm just asking, is there going to be are these notes on how to do the
Yeah, I'm going to put them
algorithm?
up today.
Are they going to be posted anywhere, or should we just go through
I'll put them on the website. I'll put them on the webpage today.
Cool. Thanks.
You're welcome.
And Ben, you have a question?
Yeah, may I ask, what's the relationship between the matrix and the vector space, or can we view the matrix as a vector space?
Okay, so the answer to your question is at the beginning of this slide.
Yeah.
Okay, so the meaning of the matrix is that it's expressing this list of vectors in terms of a basis for V. So for example, if V has dimension n, then this will be a k by n matrix. The number of columns correlates to the dimension of the vector space.
Okay.
But I'm not saying that the matrix is a vector space. I don't know what that means. I mean, the relationship between the matrix and the vector space is extremely clearly described right here. This is the thing you need to understand.
Yeah. Okay. Just another quick question. Yeah. Will you post the result of today's quiz on the quarter? Will you post today's quiz results on the website?
No, there's a pattern in the way I work. I don't give you the answers to the questions. I don't believe that that's helpful for anyone.
Okay, thank you.
Just think about the answers, right? It's mathematics. If you can find the answer, you should be able to prove that it's correct. There shouldn't be. In fact, I have always been of the opinion that we shouldn't have marking of assignments. You guys should be able to mark your own assignment. You can follow logic, can't you?
Oh, okay, thank you.
This is not a popular opinion in the math department. Okay, go on. Dick Shant, I think, has a last question.
Yeah, so I just wanted to kind of understand the significance of so in the end, when we get that final the 1 1 1 1 vector, so that kind of reminded me of the mapping we did in the beginning of the lecture with identity maps, or trying to map, this is how we reduced maps as well in the beginning. So I'm just trying to understand what significance does this have? How is this helping us? What are we achieving by doing this to the original matrix?
Well, you saw my list of purposes, right? You saw that it allows you to answer all these questions. Okay, it's the method of solving equations. Okay, so I didn't explain how that works yet, but what I'm telling you is that this simple Rubik's Cube operation is how you solve all systems of linear equations. It's how you figure out bases for bizarre vector spaces, bizarre subspaces. It's a way of deciding whether certain spans are the same. All of these problems can be solved using this method. The problem is you need to know how. So I'm going to do that on Thursday.
Okay.
Okay, and it's also relevant for linear maps and putting linear maps into standard form, just like we did with maps of sets. So what your observation is entirely correct. It's just I haven't gotten there yet.
Okay, thank you.
Okay, have a good week, everyone. See you on Thursday.
So one question.
One question. Okay, go on.
Constraints modify the dimension of a basis, right? So like if we have a vector space with the basis of dimension n, if we have one
vector
constraint
space of dimension n, yeah.
Yeah, then if a subspace has one constraint on it, then its dimension will be n-1, right?
That's true. Yeah. Yeah.
Okay, so like I wanted to use this during the assignment, but I didn't know how I could prove such a thing.
Well, we're getting there.
So no, yeah, okay.
Yeah, just wait a little bit, and it'll all become clear.
All right, then. Thank you.
See you later. Bye. Thanks a lot, Syed.
Have a nice day.
You too.